Welcome to the video lecture on LHopitals Rule. LHopitals Rule is a theorem that allows us to find limits of indeterminate forms. Now there's various types of indeterminate forms, things like 0 over 0, infinity over infinity, infinity minus infinity, 0 times infinity, 1 raised to the infinity, infinity raised to 0, or 0 raised to 0. These are considered indeterminate because they don't guarantee that a limit exists, nor do they indicate what the limit is if one does exist. So it's possible that if you have one of these indeterminate forms, there actually is an answer, but we don't know what it is, and that's how LHopitals Rule is going to help us. So LHopitals Rule says that if you have two functions f and g that are differentiable on an open interval a comma b containing the point c, except possibly the at c itself, these two functions may not be differentiable right at c itself. That's okay. Assume that the derivative is not 0 for all x in this interval except possibly at c itself. If the limit of the quotient of f of x divided by g of x as x approaches c produces the indeterminate form 0 over 0 or plus or minus infinity over infinity, then the limit of this quotient becomes the limit of the quotient of the derivatives, provided the limit on the right exists or is infinite. So in other words, if you have indeterminate forms of these two types, 0 over 0 or infinity over infinity, and that can be plus or minus, then instead of taking the limit of f divided by g, you can take the limit of f prime divided by g prime, and typically that tends to be an easier function to deal with, and you can then find its limit. Now notice that this LHopitals rule does not apply to indeterminate forms of these other types, but we can get around that by manipulating them to make them turn into either 0 over 0 or infinity over infinity. So even if we get indeterminate forms of these other 5 types, we still usually end up using LHopitals rule after we get creative. Okay? So let's see an example. We want the limit as x approaches 0 of e to the 3x minus 1 all over x. Now first things first, you always have to plug in your limit value and see what you're dealing with. So if we plug in 0, e to the 0 is 1. 0 is obviously 0, and then we're going to get a minus 1. So that numerator is going to be 0. And on the bottom, we're obviously going to have 0. So this is one of our legitimate indeterminate forms. So that means LHopitals rule applies, and this is what it would tell us. Instead of taking the limit of this particular quotient, we can take the derivative of just the numerator. So the derivative of e to the 3x, that's e to the stuff. So we're going to get e to the stuff back again times stuff prime. And the derivative of 3x is a 3. So derivative of e to the 3x is 3e to the 3x. The derivative of minus x is minus 1, and the derivative of the minus 1 goes to 0. So that's the derivative of the numerator. Now we're going to take the derivative of the denominator, and the derivative of x is just 1. So what LHopitals rule guarantees is that the limit of the original function or quotient will be the same answer as the limit of this new quotient. And if we plug in 0 at this point, notice that e to the 0 is going to go to 1, but we're multiplying that by 3. And then when we subtract 1, we get 2, and we no longer got an indeterminate form, and that denominator was 1 the whole time. So by taking those derivatives, we were able to get a new function that did have a limit and was easy to find by just plugging in. Now one common mistake that I see is that students want to use the quotient rule and take the derivative of this quotient using the quotient rule. And that's not quite how LHopitals rule works, because you're just taking the derivative of the top function by itself over the derivative of the bottom function by itself. You're not taking the derivative of the entire quotient, you're just taking the derivative of the two pieces. So be careful. Okay, let's try another example. Here we want the limit as x goes to infinity of x over ln of x. So plug in right away. As x goes to infinity, that numerator is going to go to infinity, and ln of infinity is also infinite, and that's because the ln graph, hopefully you remember what that looks like this, and as x gets big, so do the y values. So this is infinity over infinity, which is one of the allowed indeterminate forms in order to apply L'Hopital's rule. So we're allowed to use it, and this is what it would tell me. This limit here is the same as the limit as x goes to infinity of the derivative of the top, which is 1, over the derivative of the bottom, and the derivative of ln of x is 1 over x. Now you always want to simplify this as much as you can first before you start plugging in. So what is the same as 1 over x? Well, you can multiply by the reciprocal, and the reciprocal of the denominator is an x over 1. So if we get rid of that by flipping it over, then this just becomes the limit as x goes to infinity of 1 times x over 1, which is just x. And as x goes to infinity, this goes to infinity. And that's a legitimate answer, okay? Either your limit will exist because it's going to give you a finite answer like we got over here, 2, or your limit will not exist because it's infinite, okay? So there's our solution. Let's try another example. Here we want the limit of x squared over e to the x as x goes to infinity. So plug in first right away. Now, infinity squared is going to stay infinite, and e to the infinity is going to stay infinite. E to something really, really large is really, really large. So this is infinity over infinity, so we're allowed to apply L'Hopital's rule. So what it says is that the original limit will be the same as the limit of the derivative of the top, which becomes 2x, over the derivative of the bottom, which is going to stay e to the x. Now we can try to simplify here, but there's really nothing much to do, so let's plug in right away. 2 times infinity is going to stay infinite, and e to the infinity is also infinite. So look at what happened. We got another indeterminate form again. Well, the good news is, if you get that indeterminate form again, you get to use L'Hopital's rule again. You can use L'Hopital's rule as many times as you need to, as long as each time that you're applying it, it's because you're getting either 0 over 0 or infinity over infinity. So we can apply L'Hopital's rule again and take the derivative of this top, the derivative of 2x becomes 2, and the derivative of e to the x stays e to the x. So the nice thing about L'Hopital's rule is that each time you take a derivative, that function tends to get simpler, so it's going to be easier to work with. Now we're ready to plug in again. This time the top is just 2, so the limit of 2 stays 2, and on the bottom e to the infinity stays infinite. And what does 2 over something really, really large do? It gets really, really small. So this goes to 0. A constant over something infinite goes to 0. So after applying L'Hopital's rule twice, we were able to get a finite number, so our limit is just that 0. Okay? On the next one, when we take a look at this limit, we're ready to plug in immediately to see what we're dealing with. Now, as x goes to infinity, this first x goes to infinity. And then if we look at this sign part, 1 over infinity is going to go to 0. And sine of 0 is 0. So this is acting like the indeterminate form that we had up here of 0 times infinity or infinity times 0. Now that's not one of the allowed forms that we're allowed to have in order to apply L'Hopital's rule. It has to be a fraction. It has to be 0 over 0 or infinity over infinity. So what we're going to do is we're going to get creative, and we're going to try to turn this product, because that's what it is right now, it's x times sine of 1 over x. We're going to turn that product into a quotient. And a really easy way to do that is to flip things down to the denominator. And I'm going to flip the x because that's easier. This is like an x to the first. So if I wanted to move that x to the bottom, I could just make it have a negative exponent, because x is the same as 1 over x to the negative 1, or in other words, 1 over x. Okay, x is the same as 1 over x, or 1 over x to the negative 1. So I'm moving this x down to the bottom, but I'm keeping it equivalent. I mean, the x to the negative 1 in the bottom is still the same as an x in the top, and I'm leaving the sign of 1 over x where it is in the numerator. Now I've created a quotient, but we still need to plug in again and see what kind of indeterminate form this is giving me. If you need to, and I'm a visual person here, I like to think of this x to the negative 1 in the bottom as a 1 over x when I'm plugging in. So if I'm plugging in infinity for x, 1 over infinity goes to 0, and sine of 0 is 0. And in the bottom, 1 over infinity goes to 0, so now this bottom is 0 as well. So now we have the indeterminate form 0 over 0, which means we're allowed to apply L'Hopital's rule. So by changing this product into a quotient, we turned it into one of those allowed indeterminate forms so that we could apply L'Hopital's rule. So what we're going to do is take the derivative of this numerator and this denominator. So let's start with the top. Now this is sine of stuff, so to take the derivative of that we need a chain rule. Let's start with the derivative of sine. Derivative of sine is cosine, so this is cosine of 1 over x times the derivative of 1 over x. And you want to probably think of that 1 over x as an x to the negative 1. So the derivative of x to the negative 1, you bring down the power and you subtract 1 from the power, so it becomes negative 1x to the negative 2. So we did the derivative of the sine, and we multiplied that by the derivative of the 1 over x. Okay, so that's the derivative of the top. Now we do the derivative of the bottom, which again is that x to the negative 1. So to take the derivative of that, just use your power rule, bring down the negative 1, and subtract 1 from the power. Now definitely you want to clean this up first before you start plugging in. And notice that these two expressions on the top and the bottom are identical. So this is going to cancel out this exactly. So our simplified expression is just the cosine of 1 over x. So if I plug in infinity, 1 over infinity goes to 0, and cosine of 0 is 1. So our answer was a finite value of 1. So this original limit is actually equal to 1. Okay? It's kind of amazing how these indeterminate forms, where you might think it's obvious that the answer should be infinity or 0, it's not. It turns out to be a finite value. So that's kind of interesting. All right, let's try some more examples where we have to be a little bit more creative in terms of turning it into either 0 over 0 or infinity over infinity. So if we look at this next example, we have e to the negative x times square root of x. If we plug in infinity right away, we want to know what e to the negative infinity is doing. So think about the graph of e to the x, exponential growth. If I want to know what e to the negative infinity is doing, negative infinity is actually in this direction. And as your negative infinity gets smaller and smaller and smaller, the e raised to that gets closer and closer to 0. We're approaching that horizontal asymptote at 0. So this is actually going to go to 0. And then the square root of infinity is going to stay large. Square root of a really big number is still a really big number. So this part goes to infinity. So we have another product. 0 times infinity. Does the 0 rule, does the infinity rule, or is it something completely different altogether? That's what we have to figure out. But we can't apply L'Hopital's rule yet because it's not a quotient. So what we're going to do is we're going to look at our original function here, and we're going to see how we can manipulate it and turn it into a quotient. And the easiest way to do that is to take this e to the negative x and move it to the bottom by making that exponent positive. So now we have square root of x over e to the x. If we plug in infinity now, square root of infinity is still infinite, and e to the something big, or e to infinity, stays infinite. So now this is one of our allowed indeterminate forms. So we're allowed to use L'Hopital's rule. So to take the derivative of x to the 1/2, or square root of x, think of it as x to the 1/2 and apply your power rule. So we're going to bring down the 1/2 and we're going to subtract 1 from the power, so the new power becomes a negative 1/2. And on the bottom, the derivative of e to the x just stays e to the x. Now this is something that's kind of messy, and I would recommend cleaning it up first before you start plugging in. So here's what I would do. I see a negative exponent in this negative 1/2, so let's move that to the bottom so it becomes x to the positive 1/2. That's going to join the e to the x that's already in the bottom, and this 2 that's in the bottom can also join there. So I moved everything down, the 2, the x, and the e to the x, so there's nothing left on the top but a 1. If you want, you can change that x to the 1/2 power back into a radical. So this is 2 square root of x e to the x. Now let's plug in. So if I let x go to infinity, the numerator is just 1. And on the bottom we have 2 times square root of something infinite stays infinite, and e to the infinity stays infinite. So this is acting like 1 over something really, really big, which we know goes to 0. So this limit is 0. Okay? All right, the next example. This time we have an expression raised to a variable power, a variable raised to a variable. So if we plug in infinity right away, 1 plus something infinite is going to stay infinite. So this base is infinity. The power, 1 over x, is going to act like a 1 over infinity, and 1 over infinity gets small and goes to 0. So the power is going to 0. This is one of our indeterminate forms right here that we don't know what the answer is. Usually we think anything raised to the 0 power should go to 1, but if the base is infinite, shouldn't that stay infinite? So that's why it's considered indeterminate. We just don't know. So because it's indeterminate, we need to figure out the limit, but it's not 0 over 0 or infinity over infinity. So how do we turn it into that so that we can take the limit and use L'Hopital's rule? So this one is a little different than any of the ones we've done so far. What we're going to do is use a trick that we've used before when we've taken derivatives called logarithmic differentiation. But this time we're not doing derivatives yet. We're just going to use the logs to help us bring this power down to a level so that we can deal with it. So what we're going to do is we're going to let y represent this expression, 1 plus x raised to the 1 over x. And then we're going to take the ln of both sides, just like we would do with logarithmic differentiation. So I'm going to take the ln of the left side and the ln of the right side. Now the reason I want to do that is so that I can use properties of logs on that right-hand side and bring this power down out front. And just to rewrite it in a slightly different way, I'm going to take that x and put it in the bottom. So now this right-hand side is a quotient. Okay, so here's what we're going to do. If we want the limit of this original function here, let's find the limit of this quotient, and then we'll backtrack and figure out what that tells us about y. Okay, so what we're going to do is we're going to take the limit as x goes to infinity of this quotient. Now this isn't exactly my original function, right? This isn't actually what y was. This is actually what ln of y is. So whatever answer we get for this limit is going to be what ln of y equals. So then we'll need to undo that ln to figure out what the actual y is going to. Okay, so let's first figure out this limit. Now if you plug in infinity into this, 1 plus infinity is infinity, and ln of infinity stays infinite. On the bottom, as x goes to infinity, this denominator will be infinite. So this is now a quotient, and it's infinity over infinity, so we're allowed to use L'Hopital's rule. So what L'Hopital's rule tells us is that this limit will be the limit of the derivative of the top over the derivative of the bottom. Well, the derivative of the top, this is ln of stuff. So the derivative of that is stuff prime over stuff. So this 1 plus x goes in the bottom, and its derivative goes in the top. And the derivative of 1 plus x is just 1. So there's stuff prime over stuff. The derivative of the bottom function, the derivative of just x, is 1. So this is really just 1 over 1 plus x. We don't need that 1 in the bottom. And as I let x go to infinity, this denominator goes to infinity, and 1 over infinity goes to 0. So this limit is 0. Now remember what we said. This quotient wasn't the original expression that we started with. It was actually not what y was. It was actually ln of y. So this answer that we just got is ln of y. So how do we figure out what just y is? Well, how do you undo an ln? This is base e, right? So e raised to the 0 is what y will equal. I just rewrote this ln equation in its exponential form. And we know that e to the 0 is just 1. So this limit up here is actually now 1. Okay, so on these problems where you have to use an ln to help you out, and that's usually going to be the kinds of problems where you've got powers. So infinity to the 0, 0 to the infinity, 0 to the 0, things like that where there's something raised to a power. That's typically when we use ln's. What you have to remember is after you take the ln to turn it into a quotient and you get your answer, that answer isn't your final answer. That answer is the ln of your final answer. So you need to undo it by raising it e to that answer. Let's try another example to see how this works again. So here we have sine of x to the x, and we are letting x approach 0 from the right hand side. So sine of 0 is 0, and from the right hand side that's still going to be 0. And this power is obviously going to 0. So we have a 0 to a 0. Any of these indeterminate forms, these three, are the ones where you typically need to take the ln's first in order to make them work. So whenever you have a power involved. So that's what we're going to do on this one. We don't want that x up there. We want to bring it down, and the only way to bring it down is to have an ln in front. So we're going to let y equal this original function, and I'm going to take the ln of y on the left and the ln of sine of x to the x on the right, and then use properties of logs to bring this x down out front. Now we did this in the last example so that we could get a quotient and then use L'Hopital's rule. Unfortunately, this is not a quotient because we actually have a product, right? So we need to manipulate this a little bit more to make it be useful for us so we can use L'Hopital's rule. So I'm going to pull a trick that we did earlier. I'm going to take this x and I'm going to move it down to the denominator by just giving it a negative exponent. So this ln of sine x will stay on top, but now the x to the negative 1 is on the bottom. So what we're going to do now is we're going to take the limit as x goes to 0 from the right hand side of this quotient. And hopefully this will be one of our allowed indeterminate forms. So let's check. Sine of 0 is 0, and if we're coming from the right hand side, that means it's 0 through the positives, and that's important because ln is only defined for positive inputs. That's why we're coming from the right hand side here. So this is like ln of 0 from the right hand side. And if you think about the graph of ln of x, This is what it looks like. As I approach from the right-hand side, I'm coming down like this towards that vertical asymptote. So ln of 0 from the right-hand side is actually minus infinity. On the bottom, remember x to the negative 1 is like a 1 over x. So this is like a 1 over 0 through positives. And that 1 over something small gets big. And since we're coming through positive, it's positive infinity. So this is one of our allowed indeterminate forms. It's infinity over infinity. So we're allowed to use L'Hopital's rule. So we're going to do that, but I just want to remind you that this limit that we're finding here, this is not the final answer. This is ln of y, not just y itself. So we need to remember that when we get to the end. So let's apply L'Hopital's rule. To take the derivative of the numerator, this is ln of stuff again. So we need stuff prime over stuff. So the sine of x goes to the bottom, and the derivative of sine of x goes to the top, and the derivative of sine is cosine. So this is stuff prime over stuff. And then in the denominator, the derivative of x to the negative 1 is negative 1x to the negative 2. So we want to clean that up to see what we're dealing with. Because I have this quotient within a quotient, we've got fractions within fractions, we want to try to eliminate some of these. So what I would recommend is taking this x to the negative 2 and flipping it back up to the top. So now it becomes an x squared, and that minus can just stay in front. And that way we have this cosine x over sine x, and there's nothing in the bottom at all. So we don't even need that denominator anymore because we moved everything from the denominator up. So if you want to, you can rewrite this a little bit more clearly. We have our sine x in the bottom, we have our cosine x in the top, and that negative x squared can join that numerator because we moved it up to the top. So this is what we have. So now we're ready to plug in and see what we're dealing with. 0 through the positives. So if I plug in 0 for x, 0 squared is going to stay 0. There is a minus out front here. Cosine of 0 is 1, and sine of 0 is 0. So we get 0 over 0 again. Uh-oh, what does that mean? That means we have another indeterminate form, but it's one of the allowed versions. So we're allowed to use L'Hopital's rule again. So this one's a complicated one because not only did we have to do ln's right from the beginning, but we actually have to use L'Hopital's rule twice. So we want the limit as x approaches 0 from the right-hand side, and we need to apply L'Hopital's rule to this. So that means we want the derivative of the top and the derivative of the bottom. Now the top is a product of two things, so you need a product rule on top here. So we're going to do the first function, which is that negative x squared, times the derivative of the second function. Derivative of cosine is minus sine. So that minus is going to cancel out this minus, and we'll just get x squared sine x. Plus the second function, which is this cosine x, times the derivative of the first, which is going to be a negative 2x. And then all of that gets divided by the derivative of the bottom, and the derivative of sine x is cosine x. Remember, we're not doing a quotient rule here at all. We're just doing the derivative of the top over the derivative of the bottom. All right, now you can't really simplify this because there's not any like terms. So since I'm running out of room here, I'm just going to go ahead and plug in my 0 right away and hope that I get a finite answer, or else I get something infinite so I can stop. So let's see what we get. If I plug in 0, then this x squared goes to 0. Sine of 0 is 0, plus cosine of 0 is 1, and negative 2 times 0 is 0. So in the numerator, we get 0 plus 0, which is 0. In the bottom, cosine of 0 is 1. That's good news for us because we no longer have a 0 in the bottom, and 0 divided by 1 is just 0. So we finally got a finite answer. Now remember though, going way back to the beginning, this was not the original function that we were taking the limit of. This was the ln of that function. So this 0 that we just got is not what y is, it's what ln of y is. So to figure out what just y is, we rewrite this in exponential form. This is base e, so e to the 0 will equal to y, and that means y is just 1. So our final answer is 1. Okay, so this one is probably about as tough as they get because we had to do the ln's, and then we had to apply L'Hopital's rule twice, and then we had to remember to go back and turn this back into just y instead of ln of y. All right, let's try another example. Here we have 1 over sine x minus 1 over x. So if we plug in 0 right away, sine of 0 is 0, and 1 over 0 goes to infinity. For the second fraction, when we plug in 0, again, we get a 1 over 0, which goes to infinity, but we're subtracting these two things. So some people might think, well, that's just 0. Infinity minus infinity is 0. Well, that's not quite true, because infinity is not actually a number. It doesn't represent some final number so that you can subtract it from itself and get 0. It's kind of just a symbol for the fact that this gets bigger and bigger and bigger. So this is one of our indeterminate forms in our list right here. Okay? So how do we turn this into one of these two fractions? Well, the strategy that we're going to use here, we're not going to use ln's. We usually only use ln's when we have powers involved. When we have fractions involved, like this, that we're subtracting, the strategy that we're going to use is just to get a common denominator. We're just going to consolidate these two fractions into one by getting a common denominator. And the common denominator wants to be just these two denominators multiplied together. So x sine x. So this first fraction already has the sine x, it's missing the x. So I'd have to multiply top and bottom by x's, and x times 1 would just be x. The second fraction has the x, but it's missing the sine of x's. So I'd have to multiply by sine of x on top and bottom, and 1 times sine of x would be sine of x, and these two fractions are being subtracted. So here is my new fraction, one single fraction, and if we plug in 0 now into this, 0, x goes to 0, so this goes to 0, sine of 0 is 0, so the numerator is 0, and on the bottom, x goes to 0, and sine of 0 is 0, and 0 times 0 stays 0, so now we do have one of those allowed indeterminate forms. So by just consolidating these two fractions into one by getting a common denominator, we were able to turn it into 0 over 0. So that's good news because that means we can apply L'Hopital's rule. So this limit becomes the limit of the derivative of the top. The derivative of x goes to 1 minus the derivative of sine of x is just cosine x. On the bottom, be careful. This is a product. It's x times sine of x. So you have to use a product rule. So the derivative of that's going to be the first function, which is the x, times the derivative of the second, which is cosine, plus the second function, sine of x, times the derivative of the first, which just goes to 1. So again, there's not really much you can do here to simplify. I'll just get rid of that 1 in the bottom. So this is 1 minus cosine x times x cosine x plus sine x. So let's just go ahead and plug in and see what we get. In the top, we get a 1 minus cosine of 0 is 1. So that numerator is 0. On the bottom, x goes to 0, cosine of 0 is 1, plus sine of 0 stays 0. So in the bottom we also get 0. So that means we have another indeterminate form, which means we need to use L'Hopital's rule a second time. We still haven't reached something infinite or something finite. We still are indeterminate. So we're going to apply L'Hopital's rule again to this expression right here. So we want the derivative of the top. The derivative of 1 goes to 0. The derivative of cosine x is minus sine of x, but we had a minus in the front. So the minus would stay there, and then the cosine would become a negative sine x. So these two minuses cancel out. So the top is just positive sine x. On the bottom, be careful. This is another product rule again, x times cosine x. So we want the first times the derivative of the second. The derivative of cosine is minus sine, plus the second function, which is cosine, times the derivative of the first, which would just be a 1, plus the derivative of sine of x is cosine of x. So this becomes, cleaning it up just a tad here, we have sine x in the top, and in the bottom we get a minus x sine x, and a cosine plus a cosine is a plus 2 cosine x. So if we plug in 0, sine of 0 on the top stays 0. On the bottom, 0 times sine of 0, which is still 0, plus 2 times cosine of 0, which is 1. So this is good news because we finally get something that's not 0 in the bottom. We get 0 plus 2, or just 2, which means this is equal to 0. We didn't do any ln's in this problem, so this is my final answer. Okay? So if you have two fractions being subtracted that are giving you infinity minus infinity, just get a common denominator and then work from there. Okay, let's try another example. We have the limit as x goes to 0 through the positives of square root of x ln of x. So the reason why we need to go through the positives is because we wouldn't want to plug in any negative x's for the square root or for the ln. So that's why that little plus sign is there. If you plug in 0, square root of 0 is just 0, and ln of 0, remember the ln graph looks like this. So as I come through the values of 0 through the positives, I'm coming down this way. So this actually goes to minus infinity. So this is another one of those products. So what do we do to turn a product into a quotient? We flip. Which one of these looks easier to flip? I would say this one because it has an exponent on it. Right now it's an x to the 1/2. So what I can do is turn that into an x to the negative 1/2 by just moving it to the bottom and leave the ln of x in the top. So now if we plug in, ln of 0 through positives is still minus infinity, but x to the negative 1/2, that's really like 1 over square root of x. And as x goes to 0 right here, this is acting like 1 over 0, which is blowing up and getting bigger and going to infinity. So x to the negative 1/2 is actually going to infinity. So this is one of our allowed indeterminate forms. So we're allowed to use L'Hopital's rule. So we're going to take the derivative of the top. The derivative of ln of x is just 1 over x. And the derivative of the bottom with our power rule, we bring down the negative 1/2 and we subtract 1 from the power. So this is going to become a negative 3/2 power. All right, now you want to clean this up. If you want, you can think of this 1 over x as an x to the negative 1. So how would you simplify this? If you have an x to the negative 1 over an x to the negative 3/2, we also have this negative 1/2 in the bottom. And we can move that up to the top by multiplying by the reciprocal. So if we multiply this by the reciprocal, negative 2 over 1, this will be gone. And it's essentially giving us a negative 2 in front. So that negative 1/2 flipped up and gave me this negative 2 coefficient. So that's what happened to that. Now, how do I clean up these x's? You don't want to plug in yet because this isn't simplified. If you have two things with the same base, one on top and one on bottom, laws of exponents say you're allowed to subtract their two powers. And when you subtract, you want to either do it from top minus bottom, or you can get rid of some of these negative exponents if that's bothering you. If you want, you can take the x to the negative 3/2, flip it up to the top, and then take this x to the negative 1 and flip it to the bottom and make it positive. So x to the 3/2 over x to the 1, when I do 3/2 minus 1, that's x to the 1/2, and it's positive, and it should go in the top because 3/2 was the bigger power, and that negative 2 is still there. So after all of this simplifying, what that tells me is that what I'm really trying to take the limit of, all of this stuff turned into a negative 2 x to the 1/2, which is a square root. So all of this became that. So do that work, because plugging in right away is going to give you another indeterminate form. You definitely want to clean it up as much as you can first before you plug in. Now if I plug in, square root of 0 is still 0, and when I multiply that by that negative 2, it's going to stay 0. So this answer, this limit, is just 0. We didn't do any ln's at the beginning, so we're done. Once we get that answer, we're finished. Okay, let's finish up with a couple last examples that have those powers again. So on this next one, we're letting x go to 0 through positives. So this base x is going to 0. This power is going to ln of 2 on the top, and then ln of 0 through positives, remember, that is going to minus infinity. So this denominator is 1 minus infinity, which is just a negative infinity on the bottom and a constant on the top. What does a constant divided by something really, really big do? It goes to 0. So this power is actually going to 0. Okay? 1 over something big gets small. So this is like 0 to the 0. When you have these powers, that's when you want to do the ln's. So what I'm going to do is I'm going to let y be x raised to this ln of 2 over 1 plus ln of x, and I'm going to take the ln of the left side and the ln of this right side. And that's going to allow me to bring this whole big fraction out front. So the ln of 2 over 1 plus ln x comes out front, and it's being multiplied by this ln of x. So here's what I have. Ln of 2, let me use parentheses here, ln of x over 1 plus ln x. And what we want to do is we want to take the limit of this new quotient and then get that answer and set that equal to ln of y, and then undo the ln to figure out what the y actually is. So let's plug in 0 to see what we're dealing with. Remember that ln of 0 goes to negative infinity, and when I multiply that by the constant ln of 2, because ln of 2 is just a number, that's going to stay negative infinity. And on the bottom, ln of 0, again, is negative infinity, and when I add 1 to that, it's going to stay negative infinity. So this is one of my allowed indeterminate forms. So we're allowed to use L'Hopital's rule. So I'm going to take the derivative of the top. Now remember, ln of 2 is just a constant, so it will stay there. It's a constant multiplier. The function part is the ln of x, and the derivative of ln of x is just 1 over x. On the bottom, the derivative of 1 goes to 0, and the derivative of ln of x goes to 1 over x. So when we simplify, these cancel out, and all we're left with is that constant ln of 2. And the limit of a constant is a constant. So this is going to stay ln of 2 in the limit. Now remember, this ln of 2 wasn't y, it was ln of y. So if these two ln's are equal, the only way an ln of y can equal an ln of 2 is if the y is 2. So our solution is that this original limit must be 2. Okay? All right, let's try one more example like that. So here we have x plus 1 raised to the ln of 2 over x. If I plug in 0, 0 plus 1 is 1. So this base is 1. On the power, we get ln of 2 over 0. So that's like a constant over something getting small. And a constant over something small gets big. So this power goes to infinity. So this is another one of those indeterminate forms that involves a power. So we're going to use our ln's again. Let's let y be this whole expression, and then we're going to take the ln of the left and the ln of the right. And then we're going to bring this power down. So the ln of 2 comes out front. I'm going to wrap that in parentheses over this x, and then this ln of x plus 1 is also in the top next to that ln of 2. So here's kind of our quotient, and it's that quotient that we want to take the limit of as we approach 0. Now we want to plug in our 0 first to see if we have an allowed indeterminate form. So ln of 2 is just a constant. 0 plus 1 is 1, and ln of 1 is 0. In the bottom, the x goes to 0. So this is 0 over 0. So we can use LHopitals Rule. The constant multiplier out front will stay put, and the derivative of ln of x plus 1 is stuff prime over stuff. So the x plus 1 goes to the bottom, that's your stuff, and the derivative of that, stuff prime, is just a 1. So derivative of ln of x plus 1 is 1 over x plus 1, and the derivative of the x in the bottom goes to 1. So this is really looking like x plus 1 in the bottom. I don't need this 1 at all in the denominator, and this ln of 2 is in the top. So now if I plug in 0, I have ln of 2 still in the top, and 0 plus 1 is going to stay 1. So this is just ln of 2. So just like in the last example, this ln of 2 isn't what y is, it's what ln of y is, and therefore the only way these two ln's can be equal is if their stuff is equal. So that forces y to be 2, so our limit is just 2. Okay? So LHopitals Rule, it's a really quick, clever way to solve limits that are in indeterminate forms. You may have to modify your function either using ln's or by moving things to the top or the bottom to turn it into one of the allowable indeterminate forms, 0 over 0 or infinity over infinity. But then you're allowed to use LHopitals Rule, which is a really slick method. All right? That concludes our lecture on LHopitals Rule. Good luck.